Welcome to 8th lecture from chapter 8. We are studying VLSI design and we are studying chain delays. We started studying chain delays in lectures from lecture 8-7, the last lecture. The recap is that for a chain having more than one gates, the total delay is the sum of delay offered by all individual gates. In this lecture, we'll study two scenarios where NOT gate is driving another NOT gate and there is a chain. To start with, we have two NOT gates. Each of the two, it has a scaling factor of 1 and there is an input signal and the output load capacitance is the same as the input capacitance of the first gate. We call it C minimum. Right. So this is the schematic of the same. We have this NOT with M is equal to 1, this NOT with M is equal to 1. And since they both are symmetric gates, and we know that for a symmetric NOT, beta N is the same as beta P. We can also call it simply beta. So this has the device transconductance beta, 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 and this is also beta. It's a symmetric NOT. This also means that PMOS is R times, small r times larger compared to NMOS, so that the betas are the same. In our last lecture, we also studied that the input capacitance of a NOT, which is symmetric for a symmetric NOT, the input capacitance, we can also call it the gate capacitance, is the gate capacitance of PMOS plus the gate capacitance of NMOS. If it is symmetric, then the gate capacitance is C oxide WP L plus C oxide WN L. If it is symmetric, WP is mobility ratio times WN. If you plug it here, it becomes C oxide WNL times R plus 1, or it is 1 plus R times CGN. For this lecture, we call it the minimum capacitance. This is the minimum capacitance that this final gate is driving, and it is the same as the input capacitance of the first gate. How can we write a general expression for the delay of this chain? To find out the delay of this chain, either rise or fall time delay, in general, the delay offered by the first gate, this gate or this gate, is T0. I have omitted R, the rise or fall here, and I have omitted R or fall from here purposely to keep this expression general. Alpha P or alpha N, the same alpha, multiplied by C minimum, the minimum capacitance that we have just derived expression for. This is alpha. So neither this is alpha P or alpha N because it's a general expression. And what's about the delay for gate 2? This is alpha times C minimum, because C minimum is the capacitance seen by this gate, the input gate capacitance, because this transistor, for this transistor, even for this transistor, even for this gate, we have M is equal to 1. This means C minimum remains the same, and this final gate T2 is also driving a capacitor C minimum, so it remains the same. So the total delay is T1 plus T2. The expression for T1 and T2 is the same, and you can write it 2 times T naught plus alpha C minimum. So if we have all gates that are not and they all are in a chain and they all are with same scaling factor m is equal to 1, they all offer the same delay, whether rise time delay or fall time delay, the delay is the same. And total delay can be written as the number of gates in the chain times the delay caused by the first gate. Right? We'll keep this expression with us, and then we'll make a slight change in this circuit, in this chain. So TD, when all are with M, all gates are step of standard scaling factor M is equal to 1. This is 2 times T naught plus alpha times C minimum. Let's make a slight change in the chain now. And that change is, let's make it M is equal to 2. And let's assume that the second gate is driving a load capacitance that is 4 times C minimum. If this has a scaling factor 2, this means this is 2, this is also 2. Now we have the second gate. This first gate is with scaling factor 1, and the scaling factor is 2 for the second gate. Let's write expression for the delay in general for this gate number 1. This gate number 1, T0 is independent of scaling, and it does not scale as well, plus alpha times CL. The CL caused by this M is equal to 2 gate is 2 times C minimum, because the input gate capacitance is directly proportional to aspect ratio. If we have increased aspect ratio to 2, the input gate capacitance would also be increased by 2. So this is 2 times C minimum. And the delay for the second gate is T0. We know that this term is independent of scaling, plus alpha times, it is driving a load that is 4 times C minimum. And this alpha isn't alpha because we have this aspect ratio doubled, so resistance, this alpha is directly proportional to resistance, so this term is divided by 2. So this is 2. So even this comes out to be 2 alpha C minimum. This is also 2 times alpha times C minimum. So we see a very interesting fact here, that the delay caused by this gate with M is equal to 1 and by this gate M is equal to 2 are the same. So this expression becomes 2 T naught plus 2 alpha C minimum. This is a very important fact, that the delays caused by these gates are the same. If we have more gates in the chain, for example, if we have one other gate in this chain which is also a knot but with M is equal to 4 and it is driving a CL that is 8 times C minimum, this expression would be 3 times, because T3 would also be the same, 3 times. And if we have M gates in the chain, capital M, this TT In fact, in the book, in the next article, we call it capital N. Right. So capital N times T. This is a very interesting expression that if we have NOT gates in the chain with increasing order of scaling factors, the delay caused by each gate is the same. And finally, the total delay of the chain can be written as N, where N is the number of gates in the chain, times the delay caused by the first gate. We'll use this fact to find out some more interesting information about the optimum number of transistors and optimum number of gates in a chain in our next lecture. Thank you.